So in the previous lecture, we are done up to the presentation and the slide number 24, where we have discussed about segregation, that is a micro and macro segregation. And at this point, from slide number 25, we will talk about the defects of casting, and we will focus our discussion about the porosity in casting. So what are the casting defects? So they are actually the undesirable features which adversely affect the quality and the functioning of the casting. So I want to mean that casting defects are something that are we are not looking for, or they are completely undesirable, and they always try to push or lower the quality of the material we use, and we always try to remove these defects. So and there are quite lot of different types of this casting defects, and out of them, number one is your shrinkage defect. So it occurs when the shrinkage defects, it occurs when standard feed metal is not available to compensate for the shrinkage as the thick metal solidifies. They have a linear appearance. And they are of two types: open shrinkage and closed shrinkage. The number two is gas porosity, which is a very common type of casting defect, and it forms due to the formation of bubbles within the casting after it has cooled. So what it happens is that this occurs actually because of most of the liquid materials can hold large amount of dissolved gas, but this when they solidified, this they cannot hold gas bubbles, and when they will hold these gas bubbles after solidification that was present in the liquid phase, they turns into porosity, and they are called as gas porosity. So gas porosity may present itself on the surface of the casting as the porosity or pore may be trapped inside the metal, which reduce the strength of the metal. So here in this diagram, where I show you kind of gas porosity which is on the surface of the metal, and one more thing, I have focused morely on and we are supposed to focus morely on the porosity or the gas porosity because it's the most common type of defects. So porosity in terms of cavities caused due to the gas trap during solidification, as I just discussed, and there are couple of reasons for which it happens. So here you see the list of reasons. Number one is high pouring temperature. Number two is gas dissolved in liquid. Number three is slow solidification of casting. Number four is high moisture of mold. And number five is less flux is used. Here by flux, I want to mean that the separation between the liquid and the air in the outside. So there should be a good separation between them. Otherwise, there is a high chance that liquid can enter the system, and when the liquid will the air can enter the system, and if there will be air in the system, that means porosity will come to play. So next one is your remedies. Now we want to know how to remove this kind of porosity, and there are a couple of ways how you can remove these porosities, and these are: number one is to regulate pouring temperature. So we are not supposed to pour the liquid metal into the cast or the mold at a very high temperature. Number 2, control metal composition. So depending on composition also they may can evolve. Number 3 is increase flux properties. As I told, what is flux? Number 4 is ensure effective degassing. So we need to degas the mold because if there is a lot of gas is already present in the mold, we will end up having a lot of porosity. Number 5 is reduce moisture from the mold. So if the mold or the cast have a lot of moisture, we will have, as I said, a lot of pores in the system. So that is all about the porosity or the gas porosity. Number 3 is pouring metal defect, which is pouring metal defects include misruns, cold shunts, and inclusion. And out of the 3, misrun is a very common type of casting defect. A misrun occurs when liquid metal does not completely fill the mold cavity, leaving unfilled portions. So when you pour the metal into the casting or the mold and the liquid metal didn't fill all the corners or all the portions of the mold, you will end up having pouring metal defects. I will show you in the next slide how this different kinds of these defects look like. I will show you how misruns and cold runs and inclusions are. Inclusions are basically some impurities in the system. And the fourth one is metallurgical defect. So let's see what is metallurgical defect. They are actually of 2 types, hot tears and hot spots. Hot tears are also known as hot cracking, are the failures in the cast that occurs as casting cools. This happens because the metal is weak when it is hot, and the residual stress in the material can cause the casting to fail as it cools. So it's like it appears all because of the how we process the metal. And for all of them, for all of this different kind of defects, there are procedure and the remedies how we can remove them. And about this I will send you some video link in the practice session, for the practice session, about how to remove these defects. So going forward we will see how these defects look like. Here you can see there are some scars here, and at this position you see air bubbles are trapped inside the material. And and these are blisters. Blisters are also the kind of this air bubbles only. And these are foreign particles, that I just said, inclusions. And this is porosity. Porosity means pores, or the pores, just we discussed the pores in the system. And these are hot tears. Hot tears means this hotspot, or the hot tears, the metallurgical defects. Here you see blowholes. Blowholes are the larger, are the gas porosity, but they are larger in size. They are in bigger size, so they are called blowholes. Here you see pinholes. They are smaller in size. This is a misrun that I just told you, and which is a pouring metal defect. That means, see here, this mold or the liquid metal couldn't reach up to the end of the mold or the casting, and hence end up giving a kind of defect. This kind of defect is shift or mismatch. This is a drop, this one is swell, this is metal penetration. See, the metal has penetrated inside the in the pores of the casting or the mold. And this is a cold shunt. This is slag inclusion, wash and cuts, shrinkage cavity, and hot tears. So you see, these are hot tears. Next time if you see this kind of defect on your metal surface, you can figure out which kind of defect it is. So next we are again back to the iron carbon phase diagram that we always deal with, and we are again back to the track on the iron carbon phase diagram. And here I will talk about the effect of heating rate, but the thing is that we have already discussed about it, and I will just give you a reminder what it happened. So you see here, this is our liquid phase. From liquid phase we get some of the two-phase systems and other single-phase system. The single-phase systems are here the delta iron phase. This is gamma iron or austenite, and here at this portion you will see alpha iron or alpha ferrite, and here on this line you see the concentration of carbon which is increasing from left hand side to right hand side. So we call it as steel when the concentration of carbon is up to 2.4%. If the concentration of carbon in iron increases more than 2.4%, we don't call it as steel anymore, rather we call it as cast iron. And when the concentration of carbon in iron is around 0.76%, we call it as hypoeutectic, and from it is actually 0.76 or 0.8 something, we call it as hypoeutectic, and within the range of 0.76 to 2.14 we call it as hypereutectic steel. And as I already discussed with you in the chapter 3 I think or 2, that hypoeutectic steels are the most used. They are mostly used in the industry and for other purpose. And here is your cast iron. From 2.4% of carbon concentration to 4.3% of carbon concentration, we call it as a cast iron. And from 4.3% to beyond, we call it as hypereutectic cast iron. So let's see what will happen if I give different heat treatment to the steel portion of this iron carbon diagram. This is I hope I'm sure you are already familiar with this diagram. When you have the austenitic phase or the gamma phase of iron, and if you if you cool it slowly, you get perlite and a eutectoid phase. Then for moderate cooling you got benite, and for rapid quenching you got martensite. And if you reheat the martensite, you get something called tempered martensite. We have already broadly discussed about the texture of all of them, about perlite, benite and martensite. We have already discussed about also the mechanical properties of all the three phases. And here you can see from this top to bottom ductility decreases, and from bottom to top the strength increases for the system of martensite, tempered martensite, benite, fine perlite, coarse perlite and spheroids. Okay. So here we will talk broadly about cast iron. since we have already discussed about steel, so it's time we move to cast iron. We will see how how the effect of heat treatment on cast iron, and what are the different types of cast iron, and about the application, about the microstructure. We will discuss on these topics of cast iron. So what is cast iron? As I already said, cast iron is the portion of our iron carbon phase diagram where you have more than 2.14 weight percentage of carbon. And here at this portion, you see that we find something called a cementide, which is Fe3C, and you must have noticed in the previous phase diagram here Fe3 is the cementide. And here I want to tell you one more thing. The normal, all the most of the FeC3 or the iron carbon phase diagrams are limited up to the carbon concentration of 6.75, but the phase diagram that I'm going to discuss here is up to 100% of carbon concentration. It's not limited up to 6.75%. So here, see how it works. So as I already discussed with you, cementite or FeC3 is not a stable state, but rather it's a metastable compound. The stable state is graphite, so it will always have a tendency to jump from the metastable state to the stable state. So under certain circumstances, it can disassociate and or decompose to form alpha ferrite and graphite. And the reaction is given here. You see, this is the ferrite, and it has decomposed to alpha ferrite. And see, the carbon is in the form of graphite, which is a stable state of carbon. So let's see what are the conditions, the favorable conditions to form graphite. So graphite formation is promoted by presence of silicon in concentration greater than about 1 weight percent. So when there is more than 1 weight percent of silicon is present as alloying compound in the iron carbon system, it will promote the formation of graphite. And if there is a slower cooling rate during the solidification, that will also help in the graphitization or the formation of graphite. So in this picture, you see, in the phase diagram, you see there are all this cementite is replaced by graphite because it has considered that at certain point or under certain conditions, the cementite has converted into graphite. Okay, so there are a couple of different types of cast iron, and these are gray cast iron, white cast iron, malleable cast iron, nodular or ductile cast iron, and compacted graphite. So first we'll start discussing about the gray cast iron. And gray cast iron is the kind of cast iron where you have a certain composition of both carbon and silicon. So the composition is given here. The carbon and silicon contents of gray cast irons vary from 2.5 to 4 weight percent of carbon and 1.10 to 3 weight percent of silicon. So if we have this certain composition, we can get gray cast iron. And here is the microstructure of gray cast iron. And here is a very important thing, a noticeable thing I want to mention, is that most of the cast iron graphite exists in the form of flakes. It is something similar to the cornflakes, which is normally surrounded by alpha ferrite or perlite matrix. So here also you can see this flakes of graphite are in the alpha ferrite, in or in some of the conditions it can be in the matrix of perlite also. And let's see next all the mechanical properties it shows. So it is mechanically it's comparatively weak and brittle, and the reason behind the weak and brittle characteristic of this gray iron is due to its microstructure. Because if you see here, the tips of this graphite flakes are sharp and pointed and may serve as points of stress concentration when an external tensile stress is applied, and this makes the system behave mechanically the way it behaves. On the other hand, the strength and ductility is much higher under compressive load. And okay, but the thing is that it is extensively used. It has some wonderful properties, some special properties, and hence they are quite largely used in the industry. And first off, they are very effective in damping vibrational waves. Here in this picture, in the diagram, you see for A, it's a steel which have a very large vibrational amplitude. But when this steel is replaced by cast irons, this orange amplitude version, you see that the vibrational amplitude decreases, and it's very much advantageous for a lot of equipments to have a very low vibrational amplitude. So the base structures of machines and heavy equipment that are exposed to vibrations are frequently constructed of this material. The next one is the gray irons exhibit a very high resistance to wear. So, they have a very high fluidity at casting temperature, which allows the casting pieces to have complicated shapes, and casting shrinkage is also very low, and hence the gray irons exhibit very high resistance to wear. And the most important thing, they are very much not expensive and hence widely used. So here in this phase we will talk about different phase treatment, the different phases or different characteristics you see of this gray iron or the gray cast iron when you expose it to different heat treatments. It shows different microstructures and hence different mechanical properties depending on its heat treatment. So let's see the graph or the phase diagram. Here you see the orange portion, which is the composition range of commercial cast iron. So at this range, it is something starting from something near to 3 weight% of carbon to 4.12 or near to 4.15 weight% of carbon. In iron is the commercial range of production for cast iron. So here you see, if you cool it fast, and on the other hand, I want to say that there is no other alloying element is mixed to it. For this case, it is a pure iron and carbon system. So if you cool it fast, you get a combination of perlite and cementite, and here is the microstructure. You see, this is the perlite, the perlitic structure, and which is dipped in cementite, Next is, if the cooling is moderate, you get perlite and graphite flakes. So this black portions, this pointed black portion is your graphite flake, where the black and white or the zebra crossed microstructure is your perlite. Next, if you do slow cooling, you will get alpha ferrite and this again flake graphite. So here, this alpha ferrite, you can see the white um, crystals, and on which you will see this black areas are the flake graphites. And again, if you reheat, and this is our white cast iron, when I get this perlite and ferrite combination after fast cooling of my cast iron, I get this get this microstructure which I called white cast iron. The second type is called pearlity gray cast iron, and the third type is called, which I get after slow cooling, is a ferritic gray cast iron. If you reheat this white cast iron and hold it at 700 degrees Celsius for more than 30 hours, and more than 30 hours, and after that if you do fast cooling, you will get a combination of perlite and graphite rosette. Graphite rosette means, you see here there are some round or some shapes. These are called graphite rosettes, which are not at all like the flakes. It's a different kind of structure. And if you do slow cooling of white cast iron, you get alpha ferrite and again graphite rosettes. Now, what if you add some alloying element like magnesium or cesium? So once you add some alloying element like magnesium or cesium, and if you cool it in moderately, you get a combination of perlite and and nodular graphite. Nodular means round structure. Here you see it's round in shape, which is called nodular. You get a combination of perlite and nodular graphite. These black areas are my nodular graphites, and this stripes areas are the perlite. And this is called perlitic ductile cast iron. On the other hand, if you cool down the mixture slow, you get a combination of alpha ferrite and again this nodular or circular graphite. Here you see this white portion is your alpha ferrite, and this black portion, this area is your nodular graphite. And this kind of microstructure or this kind of combination is called as ferritic ductile cast irons. So here, after looking for about all these conditions and how they are formed, we get to know like they show different microstructure as well as different mechanical properties depending upon the heat treatment of the cast iron. So we are done with gray cast iron. So next I'm moving to the second type of cast iron, which is called nodular cast iron. So adding a small amount of magnesium or cerium to the gray iron before casting produces distinctly different microstructure and a set of mechanical properties. And graphite still forms, but in nodules or sphere-like particles instead of flakes. So here is the thing. This is our nodular or ductile cast iron, where magnesium or this cerium is used or added as an alloy. And here is a Here is a microstructure of the nodular or ductile cast iron. So here you see the metric phase surrounded by particles of either pearlite or ferrite. So this can be either ferrite or pearlite, as I just discussed in the previous slide, and this round dark shapes are the graphites. So here you see that the ductile cast iron has some nice mechanical properties, which are it have tensile strength ranging from 380 to 340 megapascal, and ductility varies from 10% to 20%. But the uses of this kind of ductile iron is very much limited, and it's used only where we need a very hard where at the same place where resistance surface without a high degree of ductility, like rollers of rolling mills. So so it's not much used in it's not used in a very high extension, but in under some particular conditions, and if we need those characteristics, like it's used in rollers of rolling mills. On the other hand, this ductile cast iron or nodular cast iron is used in producing another type of cast iron, which is your malleable cast iron or white cast iron. So what is white cast iron? It is for low silicon cast irons containing less than 1% and rapid cooling rates. Most of the carbon exists as cementite or graphite. A fracture surface of this alloy has white appearance and thus is termed as white iron. And they have the property that they are extremely hard but very brittle on the other hand. So here you see the light cementite. Here the white regions are your cementite regions, and that are surrounded by the pearlite. And applications, they are used in connecting roads, transmission gear, and automotive industry, railroad, marine, and most of the heavy duty applications this white cast irons are used. Next is your malleable iron that I just said that this this is the other type of cast iron. So heating white iron at temperatures between 800 and 800 and for a prolonged time period in a natural atmosphere causes the formation of malleable iron, and it forms it happens by the decomposition of cementite forming graphite, which exists in the form of cluster by ferrite or pearlite matrix. So here you see the microstructure, and these are the black portions are again graphite, or the temper carbon, or the graphite rosette, which is not exactly round, but it has some shapes, but they are accumulated together, and this is a alpha ferrite matrix. The white portion is a alpha iron. So so this is the malleable iron, and next one is compacted graphite iron. It's gray ductile malleable iron, and carbon exists as graphite, which formation is promoted by presence of silicon. Silicon contained ranges from 1.7 and 3.8%, whereas carbon concentration is normally 3.1 and 4%. So here you see the microstructure of compacted graphite iron, and it's worm like. This is like a worm. This graphite exists like a worm like structure, and which is intermediate between, and the properties are intermediate, and as well as the microstructure is intermediate between gray iron and ductile iron. In fact, some of the graphites are noodles. See here, some of the graphites, some are worm like and some are noodles, round sphere graphite portions. And on the other hand, it shows some very nice mechanical properties and are used in number of important applications. As per the mechanical properties, let's see what are the mechanical properties it shows. It have higher thermal conductivity. Number 2, better resistance to thermal shock. Number 3, lower oxidation at elevated temperature. So depending upon this kind of mechanical properties, they are widely used in diesel engine blocks, exhaust manifolds, gearbox housing, brake disc for high speed train, and also for flywheels. So hence here in the last slide I made a summary for the cast iron. Here all the applications and the metric structure, everything is given, so you can go forward and check it. And thank you so much for your attention. Bye.